Greetings to you exquisitely inquisitive, epically awesome friends. Yes, I'll call you friends this time. Last time I forgot that you're my friends and I called you mines, but it doesn't matter because apparently you can't really hear me anyway. So this is pretty much just for myself. Hopefully somebody will maybe hear what I'm saying and enjoy what I have to say. So anyway, well, sorry, shaking you up. So anyway, what I would like to talk about today is science. Not pseudoscience, although later in maybe another video you'll see, oh, he's a crackpot, he's talking pseudoscience, but this time around I just want to talk to you about real science and why should you care about science. Particularly I want to tell you about physics. That's something that's very exciting to me. And why should you care about physics? Well, I think that physics, what it does is it tells us about reality. You see, reality is very exciting because it allows us to understand our place in reality, who we are because we're a part of reality, right? So it allows us to understand how to focus our lives in the direction that works with reality, you see. So it's a very useful thing to understand, I'd say. So anyway, today I want to talk to you about the unified theory of everything, or otherwise known as the grand unified theory. And there's two sides of the grand unified theory, and for some reason we don't really have a grand unified theory. It's like the holy grail of science, at least of the physics community. Once we have a grand unified theory, oh, it would be wonderful. There would be dancing in the streets if we had something like that. But now we don't, because there's two conflicting systems of science in physics. And if you don't know, physics is basically the study of reality at the fundamental level. It's the study of space-time, energy, matter, motion, how things move throughout space and time, that sort of thing. So we have two conflicting systems of science, basically, and they both work. They're both real. We know that they work. They work in our computers. They work in allowing us to travel through space. Like general theory of relativity is one of the two, and what general theory of relativity tells us is that space or reality is flat, except it's flat, but it's curvy. But the curves are flat, you see. I hope that makes sense to you. It's not like the curves are flat, you know. So it's not bumpy, even though it's curvy. It's not like there's bumps on the curves, you see. So yes. So general theory of relativity tells us that, and it also tells us that, like mass. I have a accurate definition of mass here. It says mass in physics is the quantity of matter in a body regardless of its volume or of any forces acting on it. The term mass should not be confused with weight, right? So mass is not weight, which is the measure of the force of gravity acting on a body. So mass is the amount of matter, and it doesn't matter what the volume of the matter is. It's just the amount of mass. So you can have something really, really, really small, but it can be packed really tight and have tons of mass, like a black hole, for instance. Like when a star collapses, it collapses because all the gravity is folding in, it's crushing in on itself, and it can become really small, but it has a lot of mass, so it's heavy. So general theory of relativity, it tells you when you have mass, that the mass tells space and time how to curve. You see, space and time, it curves. That might sound weird, but it does. Reality, it curves. like this pin right here, it's curving all of space and time around it. Very small and it's not noticeable, but even if it was big, we still probably wouldn't notice it because we'd be curving with it. It's weird, right? But it's true. It's really interesting. And we know this is true, and we even have to set our GPS systems and how we fly off, in shuttles and whatnot. We have to sync our systems to what we know about this weirdness in general theory of relativity. So we know that it's true. It's weird, it's bizarre, but it's also pretty cool. I think it's very cool how reality is. It's not like how we think. It's flexible. It's very flexible. And everything's wavy and weird and warping in and out. So it's very interesting, don't you think? Yes, indeed. So that's one system. That's the system on a large scale. And then we have quantum mechanics. So quantum mechanics is very interesting too, but it's contrary to general theory of relativity. In quantum mechanics, which is dealing with the subatomic level, you see. It's kind of frothy and frantic and weird and chaotic, and it's like all crazy like, but it's all down in the subatomic level, and yet it also goes out in I'll get into that later, but so it's very interesting. So quantum mechanics deals with subatomic, and so when you're in this. Let's say, for instance, that you're playing pool, like the pool, you have a pool stick and you're playing pool, and in regular physics, you have cause and effect, you see, where if you hit the ball with the stick, and the ball, the cue ball, it hits another ball, and that ball bounces. Every action has an equal and opposite reaction, right? But in quantum mechanics, if you were in the quantum mechanical world and you were playing pool, you'd hit the cue ball, and the cue ball might not even move, but a ball that's all by itself might fling off the. It's really weird. I'm serious that we're talking about in the quantum mechanical realm that you have particles, not cue balls. You have particles that will. They'll jump from one place to another place without actually going through this space in between them. And there's also retroactive, like they go backwards in time. There's all kinds of very weird things going on in the quantum mechanical world. So the problem with these two things, why we can't combine them together, is we see this in like a black hole. So with a black hole, there's because of general theory of relativity and quantum mechanics, in a black hole you have what's called a singularity, you see, and the singularity in general theory of relativity tells us that the singularity should crush down, compact down so far that you have a 0 point mass. 0 point mass. It's like if there was an object. Sorry, I should have brought this up first. Like if you have an object that's going into the black hole, on the outside, if we were observing this object from the outside, we would never see the object go into the black hole. We would just see it going in and forever. And the data, the information of that object would just be stuck on the outside of the event horizon. It wouldn't ever actually go in to the black hole. But if you were that object, you would know that you went into the black hole. So it's like you could be watching that object for eternity, actually, forever. And that object would, if you were watching it from outside the black hole, that object would never ever go into the black hole for you, but it did for that object. So it's kind of like with calculus, with limits. If you've ever taken calculus, there's this idea of limits where where a number can be closing in and getting really, really close to another number, infinitesimally close, where it's just getting small. The number is getting smaller and smaller. The space in between, I should say, is getting smaller and smaller and smaller, infinitesimally small, but it never actually reaches that number, you see. And that's like the event horizon. We're watching it from the outside, and we never, ever, ever see that object go into the black hole. But with limits, we know that the object can both be going forever and ever and ever, getting close to the object, but never closing the distance. But at the same time, it is at that object. So it's the same thing. It's like there's a separation, and then there's a unity, a wholeness. So it's like it's separate, and it is that object at the same time. So with the black hole, it's the object for us backed away. We see the object not being connecting with the black hole, but for the object's perspective, it does connect. So it's like a paradox. It's almost like, if I were to say that I'm a 100% a man, but I'm also 100% a woman, that would be crazy, right? It's a complete paradox. It doesn't make any sense. Well, the same thing with going into a black hole, or with limits. You're outside of the black hole, and yet you're also in the black hole at the same time. It's very interesting. But that's what general relativity says. But then you have quantum mechanics. Well, there's no zero-point mass with quantum mechanics, because the quantum mechanics tells us that there's a what's called a Planck scale, you see. So this is the problem with combining the general theory of relativity with quantum mechanics, is that general theory of relativity tells us that the singularity would be at zero-point mass. But the quantum mechanics tells us that that you can't ever get to zero, that you can get really small, and the smallness gets to what's called the Planck scale. And the Planck scale is 1.616 times 10 to the negative 35th. 1.616 times 10 to the negative 35th, yes. So because of this paradox occurs when the object is becoming one with the singularity, but you also have the object forever separate from the singularity, right? So another problem with why we can't unify gravity and quantum mechanics is because of us. With the quantum mechanics side, we have this thing called the double slit experiment. And imagine that you have this gun, and the gun is shooting particles one by one, pew, 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 right? So the gun is shooting particles into this metal plate, and the metal plate has two long slits, right? They're like holes, but they're long and slender slits, and so you're shooting the particles into the slits, and you're not observing where the particles are going, but somehow the wall behind the plate is telling us that that there's an interference pattern, what's called an interference pattern. Okay, so it's showing us these lines throughout the wall, and even where there's no hole, you see the wall lines. So it's like the particles are going through the wall almost, but that's not what's going on. The interference pattern is showing us that it's giving us the exact pattern that you would think would happen if the particle was a fluidic wave, you see. So with a fluidic wave, you would have what's called an interference pattern. So it's almost like a fluidic wave is going through these two slits, not a particle, but a fluidic wave. So you'd think that it would be something like a rock going through the two slits, but that's not what's happening. Somehow this particle is becoming a wave. So we're like, oh, so particles aren't particles and they're waves, is what you would assume, right? But when you actually put a device up and you watch, like a camera or something that watches the particle as it goes through, we see the interference pattern doesn't happen. No, weird. So the interference, it's like the particle knows that it's being watched, so it's like it's shy. How is a particle shy? I don't know. It's very weird, but it happens. So when the particle is being watched, it gets like stage fright, and it doesn't want to do the wavy, cool thing anymore. It doesn't want to be all magical. It wants to be its particle again. So it's just it just goes flat on the wall like one particle instead of being the cool wave that it was before. When you weren't watching, it got stage fright. How does a particle get stage fright? That's the weirdest thing, but it happens over and over and over again. We see it happening in experiment after experiment, where if you don't watch it, we have a wave, but if we do watch it, we have a single particle. So it's like, it's a probability wave is what it's called. And in actuality, this probability, every single particle has a probability of being in all different places at once. Like all the particles in your body, all the particles in my body are spread out all over the universe. The probability, we have a real probability of the particles being spread out all over the universe. This is a real thing. Sounds crazy, but you can actually have your body be what's called superposition. This is also true in science. We've seen it happen again and again, and where we actually even have documented pictures where you look at a particle and you see the particle in one position, but you also see the particle over here and over here and over here, and you think, oh, that's nothing, it's not weird at all, because you're thinking that it's several different particles, but it's not. It's one particle in many different places, and the mind can't even figure that out, you know, like how can something be here and there at the same time? You know, you don't even think of it as being weird, probably because the mind can't even connect to something that weird. It's just too absurd to even consider the possibility of something that weird actually being true, but it's true. So you can. That's what the probability wave is, how the particles are going to that one particle is going to several different places all at once, and it's creating a wave pattern because it's in superposition. It's not just in one position, it's in multiple positions at once, what we call superposition, or what physicists call superposition. So the problem with this when it comes to the grand theory of everything is that if you don't know where the particle is, then you can't determine the gravity of how the gravity is going to act from that particle on several different things. And if you don't know that, then you don't have a grand theory of everything. We can't combine general theory of relativity. You can't combine these two theories, even though we know that they're true, even though we've seen them in the lab over and over and over again. We can't combine them yet. So that's the problem of the grand theory of everything. So that was I hope you enjoyed that. Oh, I enjoyed that so much. That was a lot of fun talking about that. So I think that's about it for today. So have a good, whatever time it is for you. Have a good one. Okay, goodbye.